This was built upon the reasoning capability of large language models. However, relying solely on these LLM-driven robots can make us some problems, as the user can give uncertain commands unintentionally, like put a ball in the microwave in this scene. Putting a metal ball in a microwave can make us some spark or damage to a ball. So to this end, we give our research question on how we can enhance the reliability of LLM-driven robots. In this paper, we focus on handling the uncertainty in human languages. In particular, we aim to detect the uncertainty in user commands and give a feedback or explanation about uncertain scenarios. So this is the pipeline of the proposed method. We first get user command and scene description by vision models, and then estimate uncertainty from the large language model. If estimated uncertainty is higher than the threshold, we classify the command as if it is infeasible or ambiguous. If the command is classified as ambiguous, we proceed to a disambiguation progress where we ask the user to help the robot to get the further information about their commands. To estimate the uncertainty from black box large language models, we first hypothesize that if the user command is uncertain, it will be more likely for large language models to generate more diverse outputs. So we first, as the framework is built upon in-context learning framework, we first start by shuffling the order of future prompts, which we call as stochastic context sampling here. We then sample the LLM generation. To quantify the uncertainty, we calculate the distance of these sample outputs on the embedding space. So if the estimated uncertainty is higher than the threshold, we then classify if the command is ambiguous or infeasible by prompting the large language model and parsing their answers. And if the command is classified as ambiguous, we further process on disambiguation progress. We first generate the reason for the uncertainty and then generate the question to ask the user to give a further information to clarify their commands. So we first conducted our experiment on pick-and-place simulation environment. For example, if a user gives a command that is ambiguous, like put a block the user wants in a red bowl, then the estimated uncertainty will be higher than the threshold, and ask the user to specify which block they would like to put in a red bowl. And when the user gives the feedback, the uncertainty drops below the threshold, and the robot successfully executes the action. In this environment, we have defined 8 different types of CLARA commands and 4 different types of ambiguous commands. We have estimated uncertainty for each command and measured the AURC between them. We have observed that there was the proposed method has 3% increase on AURC compared to a normalized entropy-based method, even without the access to the token-wise probabilities. In addition, we have observed that there was a 10% increase on AURC with stochastic context sampling. Next, we have created a new data set called Situational Awareness for Goal Classification. This is the sample of the data set. So the data set consists of pairs of scene description, robot capability, human language commands, and the uncertainty type labels. And the uncertainty type labels are defined as clear, ambiguous, and infeasible. So this data set was created based on large language model alongside with the human validators. We have measured the classification accuracy on this data set. We have observed that the proposed method outperforms the 2 different baselines, which was zero-shot and few-shot based prompting approach. We believe that estimating the uncertainty helped the model to filter out the uncertain comments to improve the classification accuracy. So this is the example of the generated output. For ambiguous goal like create a delicious meal, the proposed method successfully classified it as ambiguous and asked the user to specify what type of meal they would like to have. And for infeasible goal like solo mass problem, it successfully classified it as infeasible. And we have also demonstrated the proposed method in real-world handover scenario. We first gave an ambiguous goal, like give a Coca-Cola can to a person wearing a black shirt. But as you see, there is two people who's wearing a black shirt in the scene. So in this case, the uncertainty gets higher above the threshold and asks the user to specify the position of the person who's wearing a black shirt. In this case, we have told the robot that she's on the left. After that, the uncertainty drops below the threshold and successfully grabs this Coca-Cola can and give a person who's wearing a black shirt on the left. We have also demonstrated the proposed method from the infeasible goal, like through a Coca-Cola can. In this case, the proposed method successfully classified the commands as infeasible and does not perform any action. For summary, we have three key takeaways. We have first introduced a method to capture uncertainty from large language models to recognize ambiguous or infeasible commands. Next, we proposed a framework to classify the type of uncertainty in user commands and to proceed disambiguation progress. Finally, we presented a dataset consisting of pairs of high-level command, same description, and uncertainty type labels to evaluate the uncertainty type classification. So if you're interested in our work, please visit our project page for more details, and thank you for listening.
Thank you very much. So are there any questions, comments? Okay, I have one question. So you have two types of thresholds, right? Thresholds for uncertainty and
Just the uncertainty for the
oh, just one. Okay, one threshold. So how did you decide it?
So we had like a subsample set of the clear commands, and we estimated uncertainty from that sample set, and then set it a threshold for the. So we fitted that into a CDF, and we have set it the threshold for 80% there.
Okay. So it's fixed threshold.
Yeah, exactly.
Okay. Probably depending on the tasks, it should be changed or adapted.
Yeah. So like we had so for each task, like so we had like 3 different experiments. So for each experiment, the threshold are different. So we just sample a little bit of sub-samples there to calibrate our uncertainty.
Okay. Okay. So any other questions? Okay. So let's thanks again.